Okay, so in this video we're going to talk about integration by U-substitution, or just basic substitution, or just substitution it's sometimes called. Usually the variable we use is U, and that's why it's called U-substitution. I think it's the most well-known name. But it's one of the most basic, typically the first technique of integration that you learn in a first-year calculus course. Here's the formula right here. We're going to derive this, see where it comes from and why it works, and then do an example. But it works backwards from the chain rule. The fundamental theorem of calculus, part 1, tells us that integration and differentiation are inverse operations, that they undo one another. The derivative of the integral is the integral of the derivative, which is the original function. And this, with an arbitrary constant coming along, of course, we can see him right there. Never forget the plus c. But this tells us that every time we learn a way of taking derivatives, or every time we know something about derivatives, like the chain rule, this gives us Okay, in this video we're going to be talking about integration by substitution, or U-substitution. I think it's typically called. U, for some reason, is the variable that we use for substitution most often, and so we call it U-substitution. But it's the most basic and one of the first, typically the first technique of integration that you learn in a first-year calculus course. This is the formula right here. We're going to derive this, see where it comes from and why it works. And U-substitution, it works backwards from the chain rule. The fundamental theorem of calculus, part 1, tells us that integration and differentiation are inverse operations. The derivative of the integral is the integral of the derivative, and vice versa. And what this tells us is that every time we have a rule for derivatives, like the chain rule, we know something about how to take derivatives. This can give us a way of taking integrals, right? We can work backwards from this and get a way of taking integrals, and that's exactly what U-substitution does. It works backwards from the chain rule. Later we'll see integration by parts working backwards from the product rule. But what does the chain rule say? The chain rule says that if I have a composition of functions, f of g of x, and I take the derivative of this, it's equal to f prime of g of x times g prime of x. And this is something that we learn in high school. Fundamental theorem of calculus, part 1, says that the integral of the derivative of a function, so not of f of g, but just f of x for any function f, integral of f prime of g of x dx is equal to f of x plus a constant. And of course, here f prime of x, although we're using this prime shorthand, is understood to mean the derivative with respect to x of the function f. And so we can combine these two things. How can we combine them? Well, if we see that taking the integral of a derivative gives us the function back, well, we can think about what if we took the integral of this derivative. It's going to give us that original function back plus a constant. So we know, combining these, we know that f of x, or I'm going to use f of g of x here, f of g of x plus a constant is equal to, using these, combining these two things, it is equal to the integral of the derivative of f of g of x, the integral of the derivative of this with the dx there. And chain rule says that this derivative is the integral of f prime of g of x times g prime of x dx. And so, and this is where our substitution formula comes from, is that if I see something which is of the form integral of the derivative of some function evaluated at some other function, and then multiplied by the derivative of that function, I know this is equal to the composition of the antiderivative of that f function evaluated at that g function plus a constant. And we'll do an example of this immediately to make it clear what's going on. So suppose we'll do a pretty obvious example to illustrate the technique. but they're typically not going to be so obvious. Typically, you're going to have to do some rearranging. There's going to be some kind of trick or something that you need to do, and we'll cover that in the examples. But here, we're just going to look at a pretty straightforward example. So suppose I have the integral of secant squared of sine of x times cosine of x dx. What's this going to be? Well, and let me move this down a little bit so we can write out our relationship up here. Well, I know that secant squared of x is the derivative of tangent of x. It's tangent prime of x. And I know that sine prime of x, whoops, that's a kind of messy prime symbol. Sine prime of x is cosine of x. So if I look at this formula that I have up here, I can see that in the integral down here. Actually, I'll keep doing it up here. I don't want to move it down out of the way into the space that I want to work in. I can see that f of x is like the tangent of x here, which means that f prime is the secant squared of x, and then g of x is like sine of x, and let me move this down even further out of the way to get some more room. G of x is like sine, and so g prime is like the cosine of x here. And this lets me see, using this formula, this relationship, that I can evaluate this integral. I can get rid of this question mark here. I can evaluate this integral. I see that I have the derivative of some function, the secant squared, evaluated at some function, this sine, times the derivative of that function of sine, which is the cosine. And this, according to substitution rule, is going to be tangent of sine of x, the antiderivative of secant squared, evaluated at sine, plus a constant. And indeed, if we take the derivative of that, we can see that it's going to evaluate to secant squared of sine of x times cosine of x dx. The way that I would do this, why is this called u substitution, by the way? If I saw this just sitting there on the page and I wanted to do it, because we said this is called u substitution, but then we didn't use any u's, cosine of x dx. The way that we typically do this to make it easier to see, easier on the eyes, because sometimes these are going to be pretty complicated functions. Whenever you do a substitution, it's typically to simplify the notation, make it easier to look at and think about the relationships instead of staring at this kind of confusing jumble of symbols. Well, the way that I would do this is I would say, all right, I'm going to set u of x to be equal to sine of x. This means that du by dx is going to be equal to cosine of x. And now this isn't actually what's happening. These things, these du and dx's, we talked about this in other videos, they're called infinitesimals, and they're not numbers. You technically can't divide them and multiply them and stuff like that, but you can treat them like that. You can manipulate them in the same way, and you can think about an equation like this. You can think about multiplying through by the dx, even though it's not actually what's going on. We'll get into more detail about that for people who are interested in other videos. But I can think about dividing or multiplying this equation through by dx to find that du is equal to cosine of x dx. And so I have here du, which is the cosine of x dx, and then I have this u of x is sine of x, and this allows me to simplify this notation. Although it's pretty clear because we picked this example to be simple, it's pretty clear what's going on. In other examples it might not be, and this will really help. But here I can simplify it nonetheless by saying this is actually secant squared of u du. And this makes it really, really easy to see what's going on. Well, because now this is just an integral with u as the variable. U is a function of x, and we're going to have to unsubstitute afterwards. But right now I just have an integral of a function, which I know is a standard antiderivative, a function of u. This is secant squared as a function of u du. And I know that this is, because I know all of my all of my trig derivatives, which are really, really important. They don't emphasize that enough in high school. You need to know them all, and we have videos on that. It is tangent of u plus a constant. Of course, I have to unsubstitute this, because when I look at something like this up here, secant squared, integral of secant squared of sine of x times cosine of x dx, this is saying find me the antiderivative of this pretty complicated function of x. I can't give them a function of u. I can't say, oh, well, the integral is tangent of u plus c. And they say, well, what is tangent? What is u? And what is the relationship to x? I have to at the end, with indefinite integrals, you don't have to do that with definite integrals, and we'll see in the videos about that, why that's the case. But here I do absolutely have to put back in sine of x for the u. This becomes tangent of sine of x plus a constant. And of course, we can check by taking the derivative that this actually will give us, if I take the derivative of this function, it actually is going to give me secant squared of sine of x times cosine of x.